Yeah, so I'm super excited to be here. This is my first time giving this presentation, so feel free to interrupt and ask questions. I'm going to try and keep the math at a minimal level and mostly hand wave through some proofs by just kind of giving examples. But this is work that I did during an internship at Microsoft Research with Chingan, Edith, and Felipe, and then also with the Cloud Operations Research team for a reason that you'll find out in a moment. So I did my PhD in an operations research department at Cornell. And one thing that during this internship they were really interested in is Microsoft has a program called Microsoft Azure, which is their large scale cloud computing platform. They have data centers all across the US and Canada, even in Europe. There's one in Montreal that I was connecting to yesterday to run some code. And one thing that they're interested in is trying to optimize the way that they make their allocation decisions for the server. And this is important because if you reduce the number of resources that are used, even by 1%, you end up saving $100 million a year just in energy cost alone, right? And so they have an entire team of 40 people whose one task is to optimize this system, right? And recently, there's been kind of a call for using tools for machine learning for these kind of core operations optimization problems. And so here on the left, I have a toy picture of a scheduling problem. We have 4 servers. Letters are going to be people's code requests, and the numbers correspond to how long each person is asking for the server. So 2 days, 1 day, or whatever. And at the moment, Microsoft is using a heuristic algorithm. And for the heuristic algorithm, you can think of it as something like first fit. So you assign the job to the server that doesn't have any jobs on it. So you would assign the next job to this server here. And this is great because it's intuitive. Microsoft, when they're having meetings with their high-level business organizers, they can say this is the algorithm they're going to use. They understand it, they accept it, it makes sense. And also from an operations perspective, we show that these types of algorithms are optimal in certain simplified assumptions, right? So we know that if the jobs don't have lifetimes and so on and so forth, this is the optimal thing you can do. But it's restricted, right? Like it's only optimal if those quote unquote reasonable assumptions are true. Okay. Now, in contrast, people are really interested in using kind of data-driven decisions using a technique that I'll talk about called reinforcement learning. The reason we like this is it scales. So here I have 4 servers, but Microsoft obviously has 40,000 servers, right? And then also you can kind of modify the way that the algorithm is set up to kind of optimize any performance measure that you care about for the system. So this first fit algorithm is optimal if you're minimizing number of used servers. What if they care about something different? It's unclear if first fit is optimal in that scenario. The issue, though, is that oftentimes their naive implementation just does not work. So here I have a table comparing the performance of 2 algorithms. The orange one, this row on the bottom, is what Microsoft is currently using. The numbers are going to show 0 because they will not allow me to show actual numbers. And so I'm going to show differences relative to that algorithm. And here on the top, I'm plotting just like a generic, take a standard machine learning algorithm, run it on this problem and see what happens. And we see that across 4 of the scenarios, it actually does worse than that team. And that's good for Microsoft, right? Like 40 people are employed to develop this, right? And so me coding around on my laptop for a month, like should not do better, right? So that's somehow good. But there's this question of like, okay, how can we improve this to minimally match, but hopefully improve, right? And from a kind of theoretical perspective, and what we'll see today is that oftentimes what these algorithms are missing is a modeling the impact of the decisions that the algorithm is going to make. And so specifically in this problem, all of the simulations are determined by independent random events. Those random events are each day, one of us goes online, right? Says, I want a cloud server for 1 day. You want it for 2 days. You want it for 3 days, right? Somehow we're all independent events. And so like, how can you take that modeling assumption and use it to improve the algorithm? so that you're able to improve upon the heuristic that they're using. And this idea is not unique to scheduling. For inventory control or revenue management problems, there's a similar idea where the only randomness in the system is very simple and like structured. And so how can you take that structure from the randomness in order to improve the algorithm?
So I have a short question.
Yeah.
Are those results coming from simulations or they're particularly the real?
These.
Yeah.
Yeah, so these are from, they have layers of simulations. So they have a test bed where they do A/B testing on their actual system.
Okay.
And so these are not actual, this is on the test bed. Yeah.
Okay.
At the end, I'll talk about simulations on the different levels of realness. This is the closest to real that you can do without actually using it. They didn't want to use it because it's not good, right?
So the standard RL is some sort of, production level RL algorithm?
Yeah.
Or some sort of
A level of production level RL algorithm that they have a team of people in Microsoft research testing out whether or not they could implement.
Is the requests that are being sent, they might have a pattern, right? Over a period of months, same people would be sending some kind of request.
Very good question. I'm gonna be super relaxed about it. We don't need independent.
Okay.
We need independent of the decisions the algorithm is making. And so it could be correlated, and I'm not gonna talk about that at all, but in your head, as you see stuff, be like, oh yeah, this works for correlation. Yeah, I'm gonna be lazy about it when I'm writing it up. Yeah. Okay. And just want to kind of emphasize that these examples are not unique to cloud service computing. So people are using these types of algorithms in a wide area across operations, including inventory management, inventory control, and supply chain optimization. This is an article about Microsoft research for data center specific AI. And then also I have a colleague who's been using this for poaching prediction algorithms as well.
I remember, I think that Google also implemented several years ago some reinforcement learning model to control perhaps the cooling systems of their data center.
Yeah.
Pretty sure Microsoft has something similar now.
Yeah. So people like these companies are using RL in different components of it. And so Google is doing it for like the hardware side of things, but not the like actual scheduling algorithm per se. Yeah. So we're interested in the scheduling component and not the low level.
The question I have is, do you think there is some correlation between both?
Oh, yeah. So it's quite difficult to figure out how to like run tests to actually check. Because if you're like doing a data-driven algorithm on top of another data-driven one, you have to wait for both of them to converge. And I haven't actually seen any research on that. And I think it's an interesting question. And again, we're not going to talk about that when we show the results. Yeah, that's a good question. Yeah. Okay. And I just want to emphasize that all of these examples ended up requiring strong modifications of these like off-the-shelf production level RL algorithms to even work. Okay. So the main question that we're going to talk about today is how can we efficiently and effectively use data that you have available? So Microsoft has servers upon servers of historical data that they can use. And the question is, how can we use that data in order to optimize the system better? And we're going to look at it in two different perspectives. One will be a statistical question. So what is the size of data that you need for improved performance? Obviously, if you have more data, your performance should improve. What is the rate? So we'll talk about statistical rates. And the second component is the efficiency. So making sure that the algorithms are implementable, right? So computationally, they're tractable. And storage, we won't talk about too much today. And I like to call these three things a form of trifecta for using these types of machine learning algorithms in OR applications, especially because as OR people, we're interested in implementing our algorithms. And so the second column is kind of what we're going to focus upon the most today. Great. So the main results, just going to flash it. We're going to show three different things. The first one, we're going to talk about how you can specify a kind of typical learning paradigm to problems that only make sense in OR. So it's not going to be wide ranging. It's going to be a very specific subset. And we're going to show that you can get improved performance guarantees that small subset of problems. Okay. Second, we're going to address an issue with this algorithm, which is that it is not computationally feasible. Okay. And we're going to implement an algorithm that is computationally feasible. Its performance is going to match it, up to an additive term. And we'll talk about what that additive term is and how we can deal with it and why I think it's small. And then second, we'll talk about how this algorithm kind of uses tools from operations research in order to make it kind of implementable for Microsoft scale systems. Okay, so we're gonna go through the pieces separately, but just wanted to give the outline. And also wanted to highlight some related work. Obviously, I am not the first one. I mean, even in this room, people are using reinforcement learning for research. So there's been core research just looking at statistical guarantees under different assumptions. But I guess mostly what I want to highlight is that I think more recently, I mean, you can see that all of these papers are within the last 5 years. People are interested at using reinforcement learning algorithms for different OR applications. And even like Andrea has this beautiful package, which I'm sure people in this room worked on, called Ecole, where they're using reinforcement learning for combinatorial optimization. We're kind of gonna switch, right? And we're gonna use optimization to improve the reinforcement learning algorithm instead. Yeah, but again, like all of these papers on the bottom are like, how can you modify these algorithms to work on like actual systems you care about? Okay. So the rest of the talk will be separated into 3 sections. First section, we're going to talk about a subclass of problems for which you can get efficient guarantees. I'm going to call these problems that are coupled with exogenous events or independent events. I use exogenous so that they could be correlated, related to your question, and not independent, but yeah. And then second, we're going to characterize the learning gains. So what about those problems allows you to improve the statistical rates that you can get and improve your algorithm's performance? And then third, we're going to address a deficiency of those algorithms, which is that in some scenarios, they're not computationally feasible, and modify them to use computational problems that we all know how to do in order to improve the learning rates as well. Okay, so I'll stop here if anybody has any questions before we start with the meets. Great. Okay. So all of this is going to be based in the first section on the framework of what's called a Markov decision process. And this is a model that's supposed to capture an algorithm that's making a sequence of decisions. And so the way that it typically works is you have an algorithm, sometimes called an agent, and they observe some states. In a cloud computing scenario, the state is how many servers do I have? What is their remaining capacity? What is the current job that I have? That's the state that you have, okay? The algorithm is going to take an action. We're going to denote the action as A. That's going to be what server am I assigning the current job to? Server 1, 2, all the way down to 40,000, right? The system transfers to a new state that's going to call ST+1. That's the updated capacities for the servers. So you assign a job to a server, so its capacity goes down. And then they observe from reward, which you could think of as how many servers are being used. And the goal is to use the data that you have available in order to learn the optimal sequence of decisions, which we're going to denote as pi star. And that's just defined to be the expected sum of the rewards that the algorithm is getting, where the expectation here is taken over randomness in the decisions. So potentially the decisions you're making are randomized. So you have 50 servers available that are all the same. So we're going to assign it uniformly at random. So there's some expectation over the decisions. And then second, we'll see in a moment why this doesn't make sense in some of our problems, but there could be randomness in the way that the state updates. So you have a new job coming in, that job is random, right? Because we don't know what its size is or how long it's going to be and so on. And so that new state is also going to be random. Okay, and people typically represent these as a form of DAG, like a causal DAG, where you have a state and your action. Those two update to the new state and also update to the reward. And typically, all of these different relationships here are unknown. And so you have to estimate them from your data in order to learn the optimal policy in the problem. Okay? So this is just a generic MDP setup. Now, what I want to argue is that this model is too pessimistic, right? I just highlighted all of these relationships and I said, we don't know anything about it and we need to estimate it from data. But we're using an algorithm for a cloud system. we know how it works, right? If we add a job to a server, its capacity is going to go down by the size of that job, right? Like it's simple. So how can we incorporate that structure into this model to see how we can kind of improve the rate at which you need to use the data to estimate the value, okay? So instead of giving the specific model, I'm gonna walk through how cloud service computing works, right? So it's quite simple. You have a set of servers, here we have 4, and they have some capacity. That's the number of jobs you can put on the server. I'm gonna say the capacity is 2. A job is going to arrive, so your state contains the current job. That's random, right? Potentially correlated to answer your question, but random. And then, so a job comes and it has some size and some lifetime. We're gonna say the sizes are all 1. This job has a lifetime of 2, just for the sake of drawing a picture. And you're gonna assign it to a machine. So you put that job on that machine, okay? And then some new jobs come, right? So you have lots of new jobs, you've made lots of decisions, updated the remaining capacity on each of the different servers, right? And then some time is going to pass. So all of these servers that you only use for 1 day, they finish and they leave the system, and the remaining jobs, their lifetime decreases by 1, right? And your goal, minimize the number of used servers over some period of time. So I just like explained a problem, and it's quite simple. We actually understand most of how this system works, right? There's only one aspect that we don't know, which is what are the jobs coming into the system, right? What is the distribution that's governing the jobs that are coming? What is their size? What is their lifetime, and so on? Yeah.
So you index everything with time. What is time here?
Oh, that's a good question. I'm also going to be lax on that for the sake of the presentation. We're going to assume time is finite for the sake of giving a talk.
But what is T, like index, is it like the?
T is going to index times that you're making decisions.
But that's also random because the request is coming.
Yeah, exactly. So you can take all of this and do it to model continuous time processes where everything is the way that it should be. Great. But I'm not going to do it for them. Yeah. Okay. So the way that we're going to specialize these particular processes is we're going to say that actually most of the system is known. That the only randomness in the system, we're going to denote it as psi. So psi is going to denote the only random component, which in this model was the job. So psi will denote, I'm a new job, my size is 3, and my lifetime is 5. And that's only random, right? But it's going to be independent of everything else in the system. And as a function of that job, like if I tell you what are the capacities of the server, what is the assignment that I made, and what is the current job, you know how the system updates, right? The job that you assign a server, its capacity goes down, the rest of them are unchanged, right? And so I'm gonna model, again, we're not gonna get into the specifics, but essentially just saying that this particular kind of unknown components of the system decompose into 2 parts. One of which is going to be known, and one of which is going to be unknown at the bottom. And so I like to think of psi as like the job type of the problem. I'm a job of size 5 with lifetime 3, and then F, which is our kind of dynamics function, is just going to update the capacities on all of the different servers. Okay. And I just want to highlight that this decomposition that I did is not unique to scheduling problems. So you can think of it in inventory control, where these models have independent demand, exogenous demand, it could be correlated. Similarly, for revenue management, you have bear classes. For cloud scheduling, you have this job type and so on. So this assumption really only makes sense for OR problems. So we definitely like took the class of problems and cut it down into only a small subset that makes sense for these types of OR applications. Okay, so I did this, right? We've accepted a model that we think makes sense, right? And the question is, why is estimating and learning these models simpler, right? Because otherwise, why are we studying them in the first place? And next up, what I'll do is talk about how this like known component actually allows you to use your data in almost like an infinite number of ways more than if you know nothing about the system. Okay. So with that, we finished the first component. we've defined these processes, which I call exogenous MDPs, and they account for these kind of coupled systems with independent events. And second, we're going to characterize the learning gains. These are the statistical benefits for modeling the known structure in the problem. So the guarantee that we're going to do is going to look like this. I'm not going to prove it, and instead I'm going to hand wave my way through an example instead to talk about the intuition as to why learning these problems are simpler. And I guess the only thing to really note from the guarantee is that DH will be the size of the data set. So as the size of the data set increases, the performance is going to improve. And you'll notice that it has no dependence on the state or the action of the system. It only depends somehow on like the complexity of the exogenous component. So, so this is the difference of the proposed policy versus optimal. Here is the number of decisions you're making. This is the size of the data set. And on the top is the VC dimension, which I'm not going to talk about at all. Okay. So instead of giving the proof, I'm going to talk through an example as to why this is simpler. So we're going to assume you are trying to, let's say you are trying to sail from, on a boat, Montreal to Toronto, let's say. And there's two different paths you can go. There's the St. Lawrence, and then there's the other river whose name I always forget. Okay. So you have two different routes, okay? And depending on the wind, right, the time that each of those different routes is going to take is going to be different, okay? So let's say on day one, you took the first route, it took you 40 minutes, and the wind was 20 knots east. On the second day, you took the second route, took you 50 minutes. On the third and fourth day, you took the first route. Fourth day, you took the second route, okay? And your goal is to decide which route is faster on average, when you're taking average over the wind that you don't know until after you get to Toronto. Okay. So yeah, here's a question. Which route is faster on average? Now, if you knew nothing about the system, okay, what would you do? You would estimate the first route by averaging over these green numbers, right? You would estimate the second route by averaging over these two green numbers, right? And then pick whichever one is better, whichever one's faster. And so the standard kind of approach, right? You would treat this wind as noise. So you have lots of different samples, and you would ignore the fact, these like gradient components that we'll talk about in a second. So you estimate the value of a route by averaging over these samples. So 40, 90, and 70, taking the empirical average, where your denominator here is only the number of times that route was taken. Okay? You estimate it, pick whichever one is faster. And you can show that in this example, that its performance will depend on the number of routes that you have. So you can imagine a scenario where there's 20 different routes, and your performance is going to get worse because the data that you have for each route is going to go down. Okay, so somehow the performance is going to scale with the number of routes that you have available, right? But this doesn't make sense, right? So if I'm a sailor, I'm not a sailor, but if I was a sailor and I knew that on the day the route was 20 knots to the east, like we have entire departments that can model the time that it would have taken to take the second route, right? We know as a function of the wind, how long the second route would have taken as a function of the wind that we saw, even though we didn't take that route. Similarly, for cloud computing, we know that if we had assigned that job to a different server, we know how the state of the capacities would have updated. We can calculate it, it's simple. And so what if I told you that we can actually calculate every single entry on this table? Because every single entry on this table is only a function of the wind and the route, and the wind you know, right? So what if I told you you could calculate these durations, how long each trip would have taken as a function of the wind and the route? And that's that F function that I defined earlier, right? So what would you do here? So previously we only had the bold numbers. Now we have the entire table. Well, just use the entire column, right? we know on the second day, we didn't take the first route, but we can calculate how long it would have taken, right? And so you average over all of those numbers, right? And so hand waving, you can see that this is going to do better because we're using more samples, and so the variance is going to be lower. Yeah, so using more samples, variance is going to be lower. And so for this, you compare over all of the data that you have of the wind, which of the two routes is going to do better. Okay? Yeah, seemed like you had a question.
Yeah, why wouldn't I see the wind of that day and estimate the distribution from route 1 and route 2 and choose the one based on the wind?
Yeah, so in order to match this into the model, we're saying that you observe the current job, but you don't observe the jobs in the future. And we're thinking of the wind here as the jobs in the future. Yeah, so the matching is a little bit strange. Yeah, but good question. So here we're saying you don't know what the wind is until after you've gotten to Toronto. But fair question. Yeah, so that's actually how you do the mapping of this to the true problem, is that this random variable here is the future randomness in the system. Okay. And you can show with this that actually the performance guarantee does not depend on the number of routes that you have available. It somehow just scales as 1 over size of the data set in a hand wavy sense. Great. And so this proof is not a full proof. And really the reason that this works is that for these types of problems, you can write the performance of an algorithm in terms of an expectation over a single random variable, which is the jobs that you have in the future, or the wind that you have in the future, or the demand that you have in the future, and so on. But you have a data set of that, right? And so why not use that data set to replace that unknown expectation over the randomness with an empirical one and just pick the best decision, right? Simple. And so this is actually the one that achieves this rate. And you can do VC with some special math that's not important. Okay. So with that, there's one issue with this algorithm that I just proposed, is that here we're optimizing over all of the decisions that the algorithm is going to make, which in the case of one decision where you're just picking a route, is simple, right? But here we're making decisions over time. And so worst case, the complexity is going to scale exponential with respect to the number of decisions that you have to make, and then also the number of servers in this example for cloud computing you have available, because that's the decision you have. And so clearly, this algorithm is great because we can show that the statistical rates are much better. They are the best that it could be for this type of problem. But the issue is that in practice, this algorithm is completely infeasible to do. So that's the last thing we have to do, is figure how can we take the spirit of this algorithm and change it a little bit so that the algorithm is implementable and we avoid some of this complexity here. Okay. So that's the last component. Last component, we're going to talk about this technique that I call Hindsight Learning, which is a paradigm for incorporating optimization in order to improve the training to make it more efficient. Okay, so I'll stop here, see if we had any questions on this result before we go on to the next. Okay. Great. So I want to kind of step back to the original problem Microsoft was interested in solving. So they tasked us with solving their virtual machine allocation, their cloud compute scheduling problem. Here I have a toy little picture on the left-hand side. Each little box is going to correspond to a server. So here I have 64 servers. Each box is going to correspond to a server. Red means that the server is full. Green means that the server is empty, and they kind of get dynamically updated across time, right? But this is not the actual size of Microsoft systems. The system state corresponds to the capacity for each machine, right? Which for Microsoft is on the scale of 10,000 plus, right? However, the exogenous component, which is the current arrival of the job, Microsoft has 6 types of jobs that you can use. So if you go on to Microsoft, you have to pick one of 6 options. And the 6 options correspond to, does this server have a GPU? What is your memory? What is your CPU? And so on, right? And so the exogenous component, the psi, is simple. It's a discrete random variable with 6 values. And that's in contrast to the system state, which is a bajillion dimensional, right? And then our goal is to minimize the number of used machines. And so, yeah, just want to highlight that really the issue is that the system state here is quite large. And so that's why the previous algorithm that I wrote down is completely infeasible to do it all. Okay. So going back to this, so in an OR department, and so the obvious question is, what computational tools do we have available to us to solve this problem, right? So let's think of one of them. So we're trying to solve a stochastic problem where the demands on each day are random and unknown, okay? But what if I told you the jobs in advance, okay? So I had some oracle that said the next 50 jobs that are going to come to the system look like type A, type B, type A, type C, type A, and so on. Okay, can we solve that problem? Right? Somehow no, it's still NP hard, right? But you can't because Microsoft has a team of 40 people that have fine-tuned heuristics, right, for solving large-scale scheduling problems. And so on a Microsoft-sized system with 10,000 machines, they have code using a subpart of GERAD that can solve these problems in like the scale of minutes. It's kind of crazy. And I am not a combinatorial optimization person, so I don't quite know all of the intricate details into how they optimized it that much. But that's like this time frame that it takes them to solve those subproblems. The issue, then comparing it to what we're trying to do, which is solve a stochastic problem where the job types are unknown, you're trying to solve it on average over a stochastic sequence of requests, right? I coded it up for fun, just to see what would happen on a small scale experiment. And I ran it for a week and it still didn't finish. Okay. So this ERM version is going to do the second type of solves, which takes a week, right? But we want to propose a solution that does the first type of solves, which only take 5 minutes. Okay. So we're going to see how we can use these types of solvers in order to change the way that the algorithm works. Okay. It's not going to be perfect, because we're not solving the right problem. We're solving a simplified version of the problem, but we're going to see how we can do it in such a way such that the loss in this component is small. Okay. So for this, I don't think I need to focus on it too much in this audience. But again, there's this question of, okay, we have a fixed set of jobs, and the question is, what is the optimal assignment in order to minimize the number of servers? And so answer to do this, formulate it as an integer program. Okay, so I'll just like flash the formulation that you can do. I'm sure all of us kind of accept that it is something that's feasible to do and write down, right? And again, that this is something that Microsoft can solve in 5 minutes. And I just want to emphasize that we're really like leveraging tools from optimization in order to solve this problem efficiently. And one thing that we've been looking at is here, I've written down an integer program. So there's a question of what happens to the theoretical performance if you take the linear relaxation instead, right? What is the loss that you additionally incur from doing the linear relaxation versus solving a true integer program, and so on and so forth. And I think that all of those questions are very interesting to see how they fit in on top of this. And the second thing I want to say is that solving this deterministic planning problem for scheduling is hard for scheduling. But for a lot of other problems in OR, solving the deterministic planning problem is simple, right? Because the LP solution is optimal, like a knapsack or a bin packing problem, right? And so the issue of this component being difficult is only like a consideration for scheduling and less so for other OR type applications. Like a lot of them, like bin packing or knapsack, like the solution is greedy, so it's even simpler. Okay. Great.
Sorry, I have a question.
Yeah.
So here it seems that you minimize over the horizon the number of machine used, but not how long you use it. Is this correct or?
Yeah, so I'm being hand wavy on the actual, so, okay,
Because for me, it's like.
yeah, it's weird, I didn't want to talk about this too much.
What was here for me since the beginning is like, what is really the metric like? Is it
Oh.
time times machines?
Yeah, so I'll talk about the metric they actually care about, and I didn't write it down, just because it's, I didn't want to go into the digression
Okay,
of a lot.
I imagine it's a very.
Yeah.
uh,
So they care about this thing called PEN, and I don't know what the acronym means, but it happens when you assign a job to an empty server. And the reason that they care about this is that when a server is empty, they turn it off, right? And so assigning a job to an empty server incurs computation, energy cost, because you have to turn the server on. And then also it's kind of weird because why would you assign a job to an empty server if you had another server that could fit it, right? And so that's actually the metric that they cared about the most in terms of this work. So it's minimized the number of times you make these called PEN quote unquote allocations.
Okay. So
That as a function, it requires like lots of what are they called, dummy variables, so I didn't write it down.
Okay.
Yeah.
In the high fixed cost of turning it on, that's all.
Yeah, exactly. And like when they are, so they're currently still running with this and they have been. I'll talk about this at the end when I talk about the experiments, but they essentially have like a suite of different decisions, quote unquote. One decision is optimized for one metric, another decision is optimized for another metric, and they have this weird weighted heuristic for their final decision that they take. So that's their quote fine-tuned heuristic that they're using. And so this is like, they've been taking this and like using it to optimize 3 different metrics, and they've added those to the suites. Yeah, so that's kind of the final thing that was.
Because I was also, sorry if I can just have a follow-up.
Yeah.
I was also wondering, if this is my goal, why don't I put everything on machine 1, then when this goes to machine 2, and this goes to machine 3?
So the issue is the lifetimes and the sizes will make that not optimal.
Okay.
Yeah, because the servers has finite capacities and the jobs. Oh, here, I'm saying they all have the same size. But if they have different sizes, then it's not optimal. Yeah, so it's like the fact that there's like different, like the servers have like 4 different things like of their capacity. It's 4-dimensional. It's like, do I have a GPU? What is my memory? What is my CPU? And the 4th one is like a priority, like it's speed adjacent. And so because of the like dimension of the capacity, that turned out to not work. Yeah. But I simplified it by saying that the jobs are, yeah. Okay. Yeah, so wanted to emphasize again that this is again only working because you know how to do this in an OR community, right? Okay, so I'm gonna hand my way through the algorithm just because I think philosophically it's easier to understand than the details. So the way that the algorithm works is we have this giant data set here of jobs, okay? And we're gonna sample some future jobs that I'm gonna call psi after t. That means all of the jobs that come after time t. And here to answer your question is why we don't need independent, because we're actually gonna take a sample, and so it automatically has the time correlation in. Yeah, good question. So we're gonna do that. And then we're gonna label that data sample with an estimate that we're gonna call Q. We're gonna take expectation over doing this process lots of times. So we're gonna sample lots of future randomness, let's say 100 times, right? For each of those 100 times, we're gonna solve that integer program, right? Take an empirical expectation and use that as your estimate for the quality of making a given decision. And the policy you're gonna take is take the decision that is the best in expectation when you're averaging over the future randomness. Okay, so again, this internal component, I'm writing it down as a max over A. That's in the generic MDP notation, but for a cloud computing example, it's that IP. And the issue is that still in our system, the number of states is crazy, right? So you don't want to enumerate over all of the different states and also enumerate over all of the different actions, and then also solve a bunch of these different IPs. And so that's where we're going to use machine learning on top of it. And like use what's called no regret learning in order to extrapolate to all of the different states. Okay, but I want to add one point here is that this thing that we're doing right here is biased, right? The reason is that we're interchanging an expectation and a maximization, right? Here we're saying, I'm making a decision now that depends on all of the jobs in the future that we don't know. When in reality, we should be solving expectation over job at time t, making the decision, expectation over job at time t+1, making the decision, and so on and so forth. So it should be a sequence of these nested expectation max, expectation max. And I'm just saying, we're gonna solve expectation max and that's it. It's like a one-step thing, okay? And so obviously by Jensen's, right, you know, oh, this is the wrong direction because it should be min. But we know that Q star is smaller than the thing that we're doing, right? Because we did that interchange. So that's a simple application of Jensen's, right? But the thing is that like, we actually don't care about estimating Q. We only care about estimating the maximizer, the argmax. So long as the argmax is preserved, that's the decision that we're taking, we can estimate whatever we want, right? And so we end up kind of quantifying this bias, which we call the hindsight bias. And that's the gap that you get where you're comparing the maximizer of the actual optimal decision versus the maximizer of the decision that we're taking. And so this is important because again, you could just measure the bias in these two quantities and the bias could be whatever it is, right? And so really all you care about is the bias and the difference between the maximizers. And so that's what we call this hindsight bias term here. And this is important because you can show in a lot of OR applications that this gap is large, but this gap is actually quite small. And so trivially, like if the maximizers are the same, so A hat T is going to be equal to A star T, well, we have Q A star minus Q A star plus Q A star minus Q A star, so it's 0, right? So if the maximizers are the same, then delta is going to be 0 always. Okay. And so really the only issue is then kind of motivating that this quantity here, this hindsight bias, is low in OR applications. And with that, yeah, the last component of the algorithm is to use no regret imitation learning with some form of function approximation to generalize over all of the states and actions through an ERM-like procedure. Okay. And I just want to highlight that this algorithm is kind of using 3 tools that are specific to our OR applications. First, we're using historical data, right? So Microsoft has a giant data set characterized into a number of types, right? And they have a histogram. So we're using that data set explicitly. The second thing we're using is optimization, right? So we're using the fact that we can solve for the optimal sequence of decisions on a deterministic like future randomness in the system. So that's that max sum decision. That's that IP we wrote down. And the third thing we're using is that we have simulators and that we kind of fundamentally know how these cloud problems work to begin with. And so for this, Microsoft has a simulator that's internal, but they just released it called Maro. So if you care about these types of problems, you can play around with algorithms for it online. So just like a GitHub package. Okay. And so going back to the main result, we already talked about the first one. The guarantee for the second one should be relatively clear, right? We're doing ERM to some extent, but we're doing ERM with an additional hindsight bias term. So that's why we have a sum here. So that's how you get the performance guarantee. And for the third one, for the efficiency, our algorithm is efficient in some sense because of the fact that we're appealing to OR computational oracles instead of solving some giant large-scale ERM problem. Okay. Yeah, and just the proof of this, I want to highlight that if you like these types of ideas, you should look into a line of work called compensated coupling. And this is essentially the work that allows you to argue that the hindsight bias is small. And so there's this question of, is the hindsight bias small for cloud computing? We have explicit bounds for what it is. And so it uses this technique called compensated coupling that I did with my PhD advisor during my thesis. And then also people in theoretical computer science do this all the time for other problems. And so this hindsight bias is known to be small for inventory control, revenue management, cloud computing, and then certain types of supply chain problems. Yeah, so, but there's still questions of like, can you extend the bounds on hindsight bias for other types of OR models? Yeah, okay, so you can show that this hindsight bias is small for many OR problems, including examples of this. And if you want another buzzword to Google, if you're interested, we also like to call them profit inequalities. And the reason we call them profit inequalities is because we're comparing against a profit that knows the future randomness versus a algorithm that doesn't know the future randomness. So that's why they're called profit inequalities. Okay, and I want to finish just by highlighting some experimental results. So this is a Microsoft cluster with around 1,000 physical machines. So it's their Seattle-based cluster that they ran experiments on. Again, we're going to compare improvement relative to a production system on number of used machines, which is your metric that I just talked about before. And again, our values are going to be normalized because they won't let me publish the actual numbers. So the first row is that standard production reinforcement learning algorithm at the top. And the second column is our hindsight learning algorithm that we just designed before. And I guess the only takeaway is that we are able to see across all of the different examples that this algorithm actually improved over the system that they were using before. And on this level of percentage points, okay? And so you saw that like across all of the different data centers, it's not uniform improvement. On 2 of them, the improvement is quite minimal. You can show that the improvement is significant statistically, but kind of unclear whether or not that's like fully trusted. And if you don't like cloud computing as much as other applications, in the paper, we also have results for bin tacking, multi-secretary, and also airline revenue management problems, where you see similar types of results. But I think that these are the most interesting. And so kind of the current state of affairs related to your question is they did not implement this algorithm fully. They did what I said, which is they have a suite of rules that they're using to make their decisions. They just tacked on our algorithm that they trained on their data set and use that in an ensemble way to make the decisions that they're doing. And I think the reason is kind of multifold. One of them is related to the question of like, what is the time for these metrics, right? Essentially, they have constraints on some of them. And so once they realize that their performance relative to one metric is bad, they'll switch over to only using the algorithm that's optimized for that metric. And they'll do it for a period of time until it's better. And then they'll switch to their more general thing. So they have a very complicated like internal system that I don't understand for their actual algorithm. Yeah. And with that, I also want to comment that one thing that I've been thinking about a lot during my PhD is, especially from an OR community, I think the COL is probably like the gold standard for this. We don't really have like an MNIST for testing the performance on different algorithms. And so I've been working on designing a test bed for implementing these types of decision-making algorithms on different applications. So I have examples in facility location, resource allocation, queuing networks, VM allocation, ride-sharing systems, inventory control. We did vaccine control during COVID, and then also some particular supply chain optimization. Inside of the notebook, you'll note that all of these examples are tuned to Ithaca, which is where I did my PhD. So for example, the facility location is with Ithaca's ambulance data. So you can play through Ithaca's, I mean, it's small scale, it's a tiny town, but you can play through all of the different settings on like Ithaca localized experiments. It'll spit out performance on different metrics as well. And with that, I'll just say the final takeaways. I guess just kind of one of the things I wanted to highlight is that these exogenous inputs, the fact that a lot of these OR problems have very specialized randomness is important, because we saw this particularly in cloud compute applications, but you can also think of it in inventory systems where the demand is random, but everything else about the system is known, or even supply chain as well. And we also saw that designing algorithms required, first off, like domain knowledge. So that's great for us in an OR community because we understand philosophically how these problems work. We also incorporated the model into the design of the algorithm, right? We saw an algorithm that was specified for these types of applications and saw statistically why it did better. And then on the third component, we derived kind of like I call it a theoretically justified heuristic, right? Because we didn't solve the full ERM problem because computationally it's not feasible. And so we saw an algorithm that solved sub-problems which are feasible as an approximation to the true optimal decision. And I've been thinking about some extensions on this. One obvious question is all of these algorithms required access to historical data of the future randomness. But in a lot of problems like inventory and supply chain, the future randomness is demand, and so it's censored, right? Because if you don't have capacity available, then the demand is going to be zero, right? And so how can you extend these ideas to censored demand as well? So I have a PhD student who's working on that at the moment. And then also I think another interesting question is improving both the hindsight bounds and also these VC dimension bounds that I can talk about if people have questions for specific policy classes like an index policy or something like that. So with that, I will take any questions, and again, want to thank my amazing collaborators and then also the cloud team, because to be honest, most of the experiments were done entirely by them, so all of the kudos should be given to them as well.